Let's get started. Okay, so the problem is now there are 195 students, so it keeps on changing. So so group formation, when did we say you have to finish group? We didn't set a deadline or anything. So first assignment will be a deadline. So select groups of 5. We have too many students, 195 students. So I'll suggest select groups of 5, and the first assignment you have to come as a group, and you have to come to the impact lab at certain hours which you will decide. Like we will open up some slots when you can come and do data collection and all that. So it will take about an hour. So you have to have space free for an hour, and you have to come and do the data collection, and that is the first assignment. Right? So before the first assignment you need to form your groups. So groups of 5. Form groups of 5. Now before you come for the first assignment, you form groups of 5. Yes, you delegate one person, or no, basically all of you have to do it. But you delegate one person who is going to do the science, right? And for whom we will collect the data. So one person has to volunteer. But all of you have to know this set of science. You have to understand this set of science. So whoever is going to do it has to learn this science. The other team members also have to learn this science because they have to understand them. Right? So I will post these links, but every sign has a corresponding link where you can go, which is, and you can see a person performing this sign. So this is father. Please go out. Right? And you can learn this. You don't have to memorize them. You don't have to memorize them. You can, if you forget while doing the data collection, you can go and look it up. Right? So all those things you can do. So you don't have to memorize them, but you have to be familiar with them. Right? So at least look at them once before you come. Now you have to perform this. You have to perform this science 20 times. So there are 20 signs, 40 times. There are 20 signs, and each signs have to be done 40 times. That will take an hour to collect all the data. So that performing the yes, you have questions? Oh, you are calling your friend. So you have to understand. You have to learn this science, and the person from whom we are collecting data has to perform this science. That is the first part. So there are 3 parts to it. So that's the first part. The second part is I will or you can make sentences by combining these words, right? 4 or 5 sentences, just think of it. Then one person should just sign those sentences. You sign those sentences, and the other 3 or 4, the other 4 will try to guess what you did. Right? Now we will keep on signing unless the people understand. The 4 other person, unless the 4 other person properly understands what you are signing, we'll keep on signing. Right? So that how long it takes depends upon you and your teammates. Right? So that is the second part. That is easy because you know all the signs, and it is a combination of what signs you already know. Right? So that sentence, and you have already you know all the sentences because you have come up with those sentences. Right? Now the third and last part of the data collection is I will give you a scenario. Right? And you will have to explain that scenario to your friends. Now that scenario may or may not have words from this list. Right? So if it does not have words from this list, you have to make it up. And you have to make up in an intuitive way. Right? So if I am saying that, okay, tell him to bring you a cup of water. Right? So then many other people might have many different interpretations, but you can say, go drink water, like those kind of signs. And this has to be continuous. Continuous means you cannot say this and then wait for 5 minutes, and then say this, then wait for 5 minutes, and then again do this, wait for 5 minutes. No. So entire sentence has to be done within 10 seconds. So 10-second long gesture you give, and just the first thing that comes to your mind, first gesture that comes to your mind. So this is without any prior knowledge. You might use words from that list, but you may not. So that is the first assignment. The entire thing will take at most an hour. Okay. So the TAs, we'll have 3 TAs for this course. I haven't decided the last one yet, so I'll have to recruit one more. So they will post in Blackboard their some time slots. So this will happen. This will start next week, not this week. This will start next week. So you take 1 week to learn these signs, right? And then you form the group and come. So this will start next week. They will pull up some slots. You select those slots and you come during those times. Okay? Now when you are coming, we'll make sure. I mean, if you are wearing something on your wrist, you have to take it off because we'll give you our jewelry. Okay? Which you will learn. So and then we'll take Kinect data. So Kinect is skeletal structure, so joint data, right? And you look incredibly skinny there in Kinect. And then we'll take the depth sensor, depth data. So if you do something like this, we can understand that you have moved your arm forward and then back. And then we'll take a video. That's it. Right. Now this data is huge. We'll make all the data available to everybody so that you can do your second, third, and fourth, and fifth assignments. So that is with respect to assignments. Do you have any question? No. So if you don't have any questions, let's start our discussion on. And let's start from where we left off. So last time we were talking about data and its attributes. We will breeze past this chapter because it's a lot of information that is very easy to understand. So we'll breeze past. So we were talking about transformations on attributes. Transformation takes only one attribute at a time as input. It does not combine attributes. It's a transformation on a single attribute. Right? And transformation is only a valid transformation if it does not convert one attribute to the other. Right? So it cannot take the nominal attribute and convert it to an ordinal attribute. So it cannot sort. Sorting is not a transformation. Right? But jumbling up letters is a transformation. So you take the word rows, ROC, and you just jumble up and make it sort. That is a transformation, right? So you take one attribute value at a time and apply transformation on it. So nominal transformation, then ordinal transformation. Ordinal transformation has to be done using a monotonic function, which means either it is continuously decreasing or continuously increasing. Why? Because it has to keep the order. You cannot change the order, right? Then interval operations, you can do ax plus b, right? Any linear operation you can do. And then ratio, you cannot do x plus b, but you can just multiply with a constant. Those transformations are valid. Now, given these transformations, there are two types of attributes: discrete attributes, continuous attributes. The basic definition of discrete and continuous is discrete variable can assume infinitely many values, but this infinite set has to be countable infinite. Right? On the other hand, a continuous attribute can take infinite values. This can be uncountable. Right? So the uncountable and countable, these are these two concepts you have to understand. So what is countable and uncountable? Yes? Both are infinite sets. Yes.
Countable has a bijection to the natural number.
Exactly. So it has a bijection to the natural number. Bijection to the natural number means every element from the countable infinite set you take, you can give it a unique natural number, 1 or 2. Right? But if you take uncountable, let's say from 0 to 1, all real numbers from 0 to 1, how many natural numbers do you need to give them some IDs? Infinite, right? And if you want to give some IDs to each real number from 1 to 2, you cannot give unique IDs. Right? So that's why the real set, even between 0 and 1, that is uncountable. You cannot count. You have to end up giving non-unique numbers to different entities. Right? So that's the idea of countable and uncountable. Then there are symmetric and asymmetric attributes. So symmetric attributes means these have two values, both are equally important. Asymmetric attributes means it has 2 or 3 or 4 values, and asymmetric attributes can also have 2, 3, 4 values, but all values are equally important. Asymmetric, all values are not equally important. An example. Example is, let's say you are taking the wristband, you are wearing a wristband, and from the accelerometer, gyroscope or EMG or whatever data you can get from the wristband, you want to identify eating versus non-eating actions. Right? Now in this case, you have two labels, two attribute values. A particular time series is either eating or non-eating. Right? Now non-eating action is not important. What is non-eating, you don't care. Whether it is walking, whether it is running, you don't care. You only care about eating actions. So eating actions are the important class. Non-eating action is not important class. Right? This is often called the rare class problems. Right? You have rare class problems. Why? Because the important class has a lesser number of examples. And you have way fewer examples of eating actions than non-eating actions. There are too many non-eating actions. Right? But eating actions are much smaller. Right? So this has direct correlation with the rare class problem. We'll talk about that in some videos, not a lot. Then there are different types of data sets: record data, graph data, ordered data. So record data are 3 types: data matrix, document data, and transaction data. You want to talk about that? Yeah, we'll talk about that. And then we have the graph data and ordered data. So all these 3 types of data are structured data. Why? Because you can use a data structure and represent them. Right? So what are the characteristics of structured data? So you have different characteristics with dimensionality, sparsity, resolution. these are terms that we need to just remember, understand, and I need to see whether you know these terms, and I am sure you do. So dimensionality, you know that however many features are there, attributes are there, those are many dimensions. And we have also spoken about, discussed the curves of dimensionality. That as the dimension increases, the amount of data that is interesting to you, or the ratio of amount of data interesting to you versus non-interesting data, that decreases. Right? So if it decreases, then there are a lot of problems. First of all, the problem is your knowledge extraction algorithms take too much time. Second, their accuracy might decrease, because you have to fish for very small amount of interesting data. Sparsity is a very important concept for many reasons. One reason is you can have efficient representations. If you know that your data is sparse, you have very efficient representations. For example, sparse matrix. Right? Instead of storing the entire matrix, n by n matrix, you just store the elements and their indices. That reduces a lot of storage. The second is, if you know your data is sparse, then you can do a lot of compression, very different compression techniques. Not only can you do compression on the data, but you can also do compression on the sensing, which means you don't even sense the data. It's so sparse that you don't even need to sense the data at high frequency. So we'll talk about that a little bit later. And then resolution means that it can mean many different things. It can mean how many samples per second, you increase the samples. It might also mean how many bits you are using to represent a particular data point. Right? So resolution has different meanings. So these are some examples of record data. This we don't need to go through. This is pretty simple on its own. So data matrix is what you have some attributes and you have some record. So and the attribute versus record matrix is a data matrix. Document data is a different type of data where you have. This is one example of document data which counts the number of terms there in a particular document. So you can also represent it using a matrix. And each entry in this matrix of a document data is called term vector. Right? So these are terms which might seem very very scary, but these are not really that important. Then you have transaction type of data. So transaction data may not have an equal number of columns. It might have different entries. So it's a collection of sets. And then you have graph data, just a graph with some nodes and edges. Ordered data and unordered data, that you know, because order matters. So if A and B are ordered data, then A, B, D, C, E is not same as B, A, D, C, E. That is an example of ordered data. Spatiotemporal data is when you have, you see in weather channels, they show hurricanes. That I like those kind of pictures, where hurricanes starts moving. Right? So there is a and those are spatiotemporal data because there are two dimensions where the data is shown. So space as well as time scale where the hurricane is moving. Right? So those are examples of spatiotemporal data. Now there are different terms related to data quality. Right? So data quality concerns with noise and outliers, missing values, duplicate data. Because as you have large amount of data, the sensors have errors. Right? So the longer you run the sensor, the longer is the possibility of having an error. And these are the different types of errors that you can have. Missing values, duplicate data. Noise and outliers are a different concept. So we'll talk about that a little bit right now. So what do you mean by noise? Now, there is a very fine line between noise and outliers. You can consider outliers as noise as well. It depends upon how you think about a problem. Often if you consider outliers as noise, you might end up with a knowledge retrieval algorithm that is suboptimal. Right? Maybe noise is something that is that tells you something about the problem, some different aspects of the problem. So noise typically is referred to as distortion, things that you don't want. So for example, if you look at a speaker, a microphone, right? If you look at a microphone, then it has a gain curve, right? So frequency versus gain. So which means it is typically a inverted cup or inverted bell. Right? So there are two tails, which means gain decreases for very low frequency and for very high frequency, and there is a middle frequency where gain is very high. So if that is the case, then for very low and very high frequency, you will have a lot of distortion. Right? So that is an example of noise in data. But then there are outliers. Outliers may not be noise. Right? So some outliers although might be noise, but outliers might suggest that you might not have considered some variants of the problem. It might suggest that as well. Missing values, there can be many reasons: sensor errors, disconnection of sensors. How do you handle missing values? Up to you. I'm not going to discuss the different methods. There's no point in discussing those. Duplicate data and skipping. Now, there are many different ways to do data pre-processing. There are many different algorithms for doing data pre-processing. We will have to talk about these algorithms because we will use them later. We will use them later and we will see what happens when we use them. So, first of all, aggregation. Right? What is aggregation? Now there is a difference between aggregation and transformation. So we talked about transformation. Right? Transformation does what? Takes one attribute value and does something to it. Aggregation takes multiple attribute values and it combines attribute values. Right? So aggregation is different from transformation. Aggregation is combining different attribute values, while transformation is working on a single attribute value. So there are many different purposes to do aggregation. What are the different purposes? First of all, data reduction. Too much data, and you don't want to deal with it. So an example is, let's say you want to analyze what happens to your blood sugar when you run. Right? What happens to your blood sugar when you run? So in that case, blood sugar changes very slowly. Maybe every 10-20 minutes there will be a lot of change. Right? So do you need a acceleration or accelerometer data every 100, so every 10 milliseconds? You don't need acceleration data every 10 milliseconds. So if you have aggregated acceleration data every 5 minutes, that suffices. So you reduce that amount of data. What happens if you reduce the amount of data without losing knowledge? Right? That is important caveat. That you should not lose knowledge about the data. So without losing knowledge about the data, if you aggregate them, then it becomes easier to analyze. Right? So data reduction is one thing. Change of scale, right? Cities versus homes. So if you think of smart grid, how many of you know about smart grid? You have to know these terms because these terms are very important for technical interviews. They'll ask you what is about smart grid. So if you use these terms, then that means that the interview whoever is asking you questions will feel that okay, this guy knows something. You just have to use the terms. Okay. So smart grid, if you and you have to say these things confidently, even like maybe banging the table. Smart grid, then more impact. So take the example of smart grid. So what happens in smart grid is that there are two sides, two components of smart grid: the transmission side and the distribution side. Transmission side is what? You have power plant, nuclear power plant, hydroelectric power plant, whatever. And from there you generate a lot of electricity in megavolts region, or megawatts region, right? Even more, right? So you generate that much amount of electricity and you go through transmission lines and transformers, and if you give a megawatt that range of electricity to a home, it will burn. So you cannot do that. You have to reduce the level of power, right? So you have transformers. Now once you reduce the level of power and it goes to kilowatts, that's where your distribution side begins, right? Or hundreds of watts. That's where the distribution side begins. So now the transmission side has to provision for power. It has to do load balancing. Load balancing means it has to know how much do you need. Whatever you need, that much power I will give to that particular household. Now the transmission side, whatever power consumption is happening at a home level, doesn't really affect the transmission side, because the transmission side is too big. What affects is, if you take 10 houses, 20 houses, 30 houses, or even 100 houses, and you combine their power consumption, then that parameter has an effect on the transmission side. Individual home, how much electricity there is consuming, doesn't have any effect on the transmission side. So transmission side deals with aggregation of these houses. Okay? So that is total change of scale. So it needs data at that particular scale in order to make decisions. Individual home level data doesn't matter to the transmission side. Right? So that is an example of change of scale. And then one thing is more stable data. Now this is important. If you take, so let me ask this. So there is a time series data, right? You have used a sensor and you have collected a time series data for a particular event. Now some malicious person adds some Gaussian noise to it, right? Following certain mean value, certain standard deviation. Mean value is easy to ignore. You just take the average and minus it, right? So you get rid of the noise. But there is standard deviation, so around zero mean it is varying. How do you get rid of that noise? Is there a way to get rid of the noise? Let's say you have 2000 hertz sampling frequency and you have collected the data for 20 minutes. How do you get rid of Gaussian noise?
Do you have any previous data we can compare?
No previous data. You just have that data. Have anybody heard about moving average? Moving average you have heard? Right, so what do? You begin after 5 samples, 10 samples, whatever you choose, initial samples, let's say X samples. You begin after X samples. The X plus 1 sample is the average of the previous X sample. The next X plus 2 sample is the average of the sample from 2 to X plus 1. X plus 3 is sample from 3 to X plus 2. Right? If a signal has Gaussian noise of standard deviation sigma and you do moving average, turns out that for every iteration of the moving average, the standard deviation reduces by square root of 2, by a factor of square root of 2. Right? So if you do moving average, it reduces Gaussian noise, which means it makes the time series more stable. Right? So that's why you do aggregation. And that is what they have also shown. Like what is the standard deviation decreases the moment you do average. So they have done with precipitation in Australia, but we don't worry about that. Now sampling is a very important concept. Sampling is used to do data selection. Now why do you do data selection? Because you want to reason about it. Right? Now there are many different theories. There are many different theories behind sampling. So the classical problem that this book uses is this. So this started the sampling theory. It's a classical problem. So there are 10 groups, right? And the question is, what sample size is necessary to get at least one object from each of 10 groups, right? So you are randomly sampling 10 groups. There are some objects in these 10 groups. Let's say P objects, right, are there in each of the groups, and you are selecting randomly. How many samples should you take so that the probability that you have at least one item from these 10 groups is nearly 1? That question started the research in sampling theory, and then I am sure you know the Nyquist sampling theorem, right? Any signal, you do the Fourier transform, you select the maximum frequency that this signal has, and you have to sample at double the maximum frequency. Now this is there is a small catch here. If you take a square wave, right, just a step wave, you know, right, from 0 it becomes 1 right at that instant, and it stays 1. Right. So if you take a step signal and let's say you do Fourier transform of that step signal, what is the maximum frequency you can have? Let's say at time t equal to 0 it was a step of 1 unit, and it remained like 1, it remained 1 till infinity. So you do Fourier transform, what is the maximum frequency that you can get? What? Why? How will the Fourier transform look like? So you have to revise, do a little bit of revision, because these concepts we will use later when we are discussing more advanced machine learning concepts or signal processing. You have to understand this. So if you take a step response, if you take a step signal and do frequency analysis on the steps signal, turns out that at 0 frequency you will have a very high peak. Then so when you do frequency response, then you select an interval, right? An interval of f. So f is your choice, maybe 0.2 hertz, 0.3 hertz, whatever, it's your choice. So if you take, then let's say we take 0.2 hertz. So at 0 there is a high peak. At 0.2 hertz there is a peak, but lower than the peak at 0. Then at 0.3 hertz there will be a peak, but lower than the 0.2 hertz peak. So it will slowly go down, but it will never be 0. A square wave has infinite frequency, so the maximum frequency is infinite. So if Nyquist says that, okay, to have an accurate representation of a square wave, you need a sensor that senses twice the maximum frequency, then you cannot sense a square wave because it has infinite frequency. Twice the maximum frequency is infinite. So you need a sensor that senses in 0 time. Right? That is not possible. So what is happening? What is Nyquist saying there? So Nyquist says that, okay, you do the frequency response, fine, but then have a threshold, right? Have a threshold epsilon. If the frequency goes below epsilon, neglect that frequency, right? Not the frequency, the power of the frequency. Okay, we are skipping a lot of things, and I am seeing a lot of lost souls. So let's explain this in more detail. I am skipping all these things because these should be prior knowledge. That's why I am not going into details. But if you need, we can discuss. Then I want to quickly go into the interesting stuff. These are very basic. So this is a step signal. We typically represent it using UT, right? This is step signal at minus t, which means anything less than 0 is 0, at 0 it becomes 1, and it remains 1 forever. Right? This is a step signal. Now what is the frequency response? What do we mean by frequency response? What do we plot in y and what do we plot along x? The idea behind having a frequency response is any signal dt or st1. Any signal can be represented as summation of sine waves. Right? I'm assuming everybody knows. Any signal is a summation of sine waves. Right? So if you the square wave can also be represented as a summation of sine waves. So what does the frequency response give you? The frequency response gives you, okay, these are on the x-axis is the frequency, on the y-axis is the power of that particular frequency. So what is the power? It's proportional to Ci square. Right? It's proportional to Ci square. That's power. So frequency response plots this. Now for a square wave, if you see the frequency response, it is like this. And it goes to infinity. It will become infinitely zero, very close to the axis, but it will never become exactly zero. So the maximum frequency that you have in this signal is infinity. Maximum non-zero frequency is infinity. So now, how do you do Nyquist plot in this case, or Nyquist theorem? How do you apply Nyquist theorem? Right? Nyquist theorem says sensing frequency should be twice the maximum frequency. So what you do is you select an epsilon. Let's say this is epsilon, and you say if the power of that particular frequency is less than epsilon, cut it off. It's not important. Cut it off. So if you cut it off, then this is the maximum frequency, omega max. So you select that sense at twice of omega max. Right? If you say sense at twice of omega max, then it is guaranteed that you will have something like this. You can represent something like this. It won't be sharp increase as the UT, but you can sense something like this. The more the frequency, the more you close the gap. But you cannot have a perfect square wave, because then you need infinite frequency. So that is basically sampling. That is how that is the sampling theory. Right? Now there is a new age sampling theory. New age means 20 years back, maybe 1980s. New age. So new age sampling theory says what? Nyquist theory you can do better than Nyquist theorem. Better than Nyquist theorem means they combine the notion of sparsity and sampling. We talked about sparsity, right? You combine the notion of sparsity and sampling. So they say that, okay, let's say a signal is sparse, right? This signal is sparse, UT. UT is sparse, right? If you take the difference, if you take differential of UT, what will you get? Differential of step is an impulse. Impulse means so if you take that, then this signal is sparse. Sparse means it has very few non-zero values. Most of the values are zero. Right? If you have that kind of a signal, if you can give me that kind of a sparse signal, then you do not need to sample at the highest, twice the higher frequency, or twice the maximum frequency. You can do much better. Right? Why? Long run story. We will not discuss. So that is called compressive sensing. So this was our Nyquist sensing, and this is compressive sensing. Taking advantage of data sparsity. So these are some concepts that, and we went kind of off topic, but that's fine to go off topic sometimes. Right? So now, if you solve this problem that we have here, you will see that you can assume different kinds of distribution, Bernoulli or Poisson, right? You can assume different types of distribution, and you can come up with an equation that says that how many samples versus what is the probability of getting one sample or one representation from each group, right? And you will see that graph, you will get that graph. I will not go into details of the derivation and all that. Curse of dimensionality. We have discussed, let's discuss a little bit more. So if you have too many dimensions, computation expensive, difficult to store, difficult to visualize. Right? It's very difficult to visualize 3-dimensional, 4-dimensional data. There are a lot of cool visualization techniques for dimensions more than 3. You can search on the web, they are good. But we are not talking about dimensions more than 3. We are talking about, now this is the age of deep learning. Right? If you have deep learning, the input is what? Inputs are images. Right? So what are the dimensions of images? Every pixel is a dimension. It can have values from 0 to 255 and times 3. Right? So every pixel is a dimension. So if every pixel is a dimension, then it has how many dimensions? 1024 cross 1024. Right? Tens and thousands of dimensions. How do you visualize that? Cannot. So it's a curse of dimensionality. If you have a lot of dimension, these are problems. Now the thing is, we have talked about this earlier. When dimensionality increases, data becomes increasingly sparse in the space that it occupies. Sparse means interesting data points are further apart, and there are very small number of interesting data points. Most of it is uninteresting, and we saw that already. So the book has this example that if you have a data point with only 2 possibilities, a grade in math and grade in physics, so 2 attributes, then total number of possible combinations is 25, which means you have each combination can appear 4 times on average. So if you have 100 students, right? On average, each combination occurs 4 times. But if you have a 6-dimensional space, which means you have 6 attributes, then what happens? Total number of possible combinations is 15,625. So if you have 100 students, right, then how many times each combination will appear? Not even 1. That's less than 1. So which means a lot of combinations don't even appear, right, in the data. So it's uninteresting points. You just they are not useful because they don't even appear in the data. So that is the problem of the dimensionality, curse of dimensionality. Because an algorithm, if you develop a knowledge retrieval algorithm, that doesn't know before running through the data, that doesn't know whether that data point exists or not, right? So even if it doesn't exist, it has to process that data point. So it processes a large number of unnecessary data points, which doesn't even exist in your records. So we have to reduce the, we have to worry about curse of dimensionality. So this again another thing that explains it. So what it says is that is the relationship between density of points and the distance between points. Okay. I'm not going to go over this example, laboring the point. You get it, curse of dimensionality. I'm assuming. Do you get it? What is curse of dimensionality? If you have problems, you can ask me, we can discuss more. So we have to reduce dimension. Now, the moment you reduce dimension, dimension is there for a reason, right? It's there for what? It's there to gain some knowledge. We install one more sensor so that we can see something new, which we haven't seen before. So if you now reduce dimension, then there is a risk. The risk is that, okay, what if I lose knowledge? Right? What if I lose knowledge? So you have to reduce dimension in such a way that you don't lose knowledge. How do you guarantee that? So if you are given 10 data streams, right? Let's say these are the 10 data streams that you are given. let's say 4, and I don't have patience for that. Let's say you have 4 sensors, right? And these sensors are giving you this kind of data points. Which one will you eliminate? Last one. Why will you eliminate last one? What? Constant. So which means it has low variation, low variance, right? Hold on to that thought. Now, yeah, another sensor that gives you this. Oh, no. That gives you this. What can you do? Which one will you eliminate? So, that's not mine. So you have now these 5 data points. So you have said that I will eliminate this. Good. Can you eliminate something else? What? Will you eliminate second and third? Or do you eliminate fifth?
You can eliminate 1 and 2, third and 5 and giving 2 classes.
Is it wise to eliminate 1 or 2? 1 and no, 1 not 1. What? 1 and 2? Why?
Third and 5 are giving us some separate classes, like kind of.
But 1 also has a variance.
Yeah.
Good variance. It has something interesting going on there. So if you eliminate number 3, no, if you eliminate number 4 by the logic that it has low variance, you cannot eliminate number 1 because it has high variance with that same logic. So now which one can you eliminate? 2, 3? Okay. So he says 2, 3, 4. And you can eliminate 2, 3, 4. That is what you are saying. Is it wise? Somebody has some other answer, or 2, 3, 4 is fine? What? 2? Raise your hand and give me an answer. Yes. 3 and 4. 3 and 4. So why? Because it's not much variance. Yeah? It's not much variance. So she says 3 and 4. Any other answers?
1 and 4.
1 and 4. No, you cannot eliminate 1 and 4 with the same logic. Why? Because if you are saying that, yes.
They are following some pattern. I mean.
So that's what we want, to get patterns. Don't we want patterns? That's the whole point of having data mining class, to get patterns.
We can eliminate everything except the last because we can see the patterns in the first 4, but the last one has some patterns. It follows from the top 4.
No, does it have any pattern from 1? Okay, what is the last one? What have I drawn? Yes? It's a summation or combination of 2 and 3, right? The last one is a combination of 2 and 3. You can do a linear combination of 2 and 3, maybe add it up, right? And you will find number 5. Right? So it has, number 5 has nothing to do with 1. So 1 is a new dimension. New dimension means it is a new data point, new data time series, which gives us new information. It says that something is periodic. You cannot eliminate 1. If you eliminate 1, then you lose the periodicity of that event. Right? So you should not lose the periodicity of that event, because that is an important knowledge. So you cannot delete 1. Right? You can safely delete number 4 because it has very less variance. So nothing happens, it's just constant. You just note the constant value and delete the times it. Right? So you don't need 4. Now the question is, since 5 is a summation of 2 and 3, do you delete 2 and 3 and keep 5, or do you delete 5 and keep 2 and 3? Right? Okay, yes, he is saying delete 2 and 3 and keep 5. So if you delete 2 and 3 and keep 5, what is the advantage? 2, you have reduced 2 dimensions, right? But what is the disadvantage? What? That is a very vague statement. You are using a lot of information. What is lot? Now how do I quantify? How much? Very vague statement. But I understand your sense, the sense in which you have made the sentence. So the sense is that you are keeping the aggregate but deleting the source. So if you keep the aggregate and delete the source, you can never get back the source. Right? If you keep the source, delete the aggregate, you can make the aggregate and get the aggregate anytime you want. Right? So if you delete the source, then you are deleting much more information. Because you can anyways get the aggregate anytime, just add them up. Right? So we have 2 different ways of eliminating dimensions now. First is low variance. Any time series that has low variance, delete that. Second is any time series that is a combination of other ones, delete that. Not time series, dimension. Right? So one dimension which has very low variance, delete that. Or any dimension that is a combination of the 2, delete that. This technique or this intuition is behind principal component analysis. Right? PCA, principal component analysis, is a very, very common technique used in signal processing in dimensional reduction. Right? That is the technique, the first technique mentioned here, principal component analysis. This is the basic idea behind principal component analysis. 2 things. I want to reduce the dimensions that are low variance, and I want to reduce dimensions that can be represented as linear combination of other dimensions. Remember, linear combination, not non-linear, right? So you cannot say, okay, one dimension is sine of the other. No, that is non-linear transformation. It has to be linear, which means ax plus bx, by, ax plus by, right? So there are other techniques as well, principal component analysis, singular value decomposition, and you can use machine learning supervised or nonlinear techniques to reduce dimension. But we will only talk about principal component analysis. Right? So let's talk about that. So what does principal component analysis do? Now here we have to understand certain terminology. Do you understand projection? No, first of all, do you understand vector? Vectors everybody understands. What is it? You can just think of a coordinate space, right? And in that coordinate space there is an origin 0, 0, and if there is a point x1, x2, you take the origin and connect the point x1, x2 and put an arrow on it. That's a vector, right? So how do you represent a vector? Is just the value x1, x2. That is the vector. You can represent it as a row or a column, right? And then operate matrix on it. Then you can apply matrix operations. What is a projection? What is a projection of a vector onto another vector? So there are 2 vectors, v1, v2, right? What is the projection of v1 on v2? Dot product, right? So you find out the dot product and then do what? No, how to compute projection? Or what do you mean by projection? A simple drawing. What you can do is so if you have 2 vectors, let's say this is v2 and this is v1, right? Then what you do is take this and drop a perpendicular on v2, right? Drop a perpendicular on V2 and this is the projection. Judge? So V1 you have to put arrows on them because these are vectors. So how do you compute projection? He was right that you could take the dot product of the two vectors, but he didn't say divide by the magnitude of V2. So if you are computing projection in the direction of V2, this is the equation, right? You compute dot product and divide by V2. So what will you get out of projection? What do you get out of projection? Value of V1 along V2, but what will you do with it? Similarity, right? He says similarity. So you can, it's a measure of similarity between the vector V2 and V1. But when you do this similarity and you only work with this, right? If you only work with this vector, then what happens to this vector? In this direction, what happens to the projection in this direction of V1? If you only argue about your problem by just considering this dimension along V2, what happens to the dimension that is perpendicular to V2? Ignore it. You are ignoring it. So you are reducing that dimension. Right? You are reducing that dimension. So keep that in mind. Now let's discuss some more concepts. You know eigenvalues, eigenvectors. Right? Everybody knows eigenvalues, eigenvectors. So basically, eigenvalues are solution to this equation. So if it's a matrix A, for a matrix A, you find determinant of lambda I minus A equals 0. A solution, so lambda is the parameter. Right? So you find out the solution of lambda. So the solutions of lambda are the eigenvalues, right? And then what are the eigenvectors? So the eigenvectors are x's which satisfy this equation. So take a matrix, multiply x with it, equals lambda x. Right? Now, what is the significance? What is the practical significance of eigenvalue and eigenvector? This is a equation. But what is the significance of eigenvalue and eigenvector? Yes? So to understand the significance, let's first understand what is this. What did we do? We took a matrix A. Now think about this, that this A is a data matrix. If A is a data matrix, then what did we do? We projected the entire data set on that direction x, right? And that entire data set is represented just by one value, lambda, right? So what does that say about the direction? So it says that the direction is encoding some information that is characteristic of A, right? There's a one characteristic information of A. So turns out that that equation lambda I minus A determinant that expression is called the characteristic equation, and it's for a reason, because the solutions lambda describe basis of that matrix, and using those solutions you can argue about a lot of things on that matrix. For example, how do you find determinant A? Determinant A is product of the eigenvalues. How do you find trace of A? Trace of A means the summation of the diagonal terms, right? It's just sum of the diagonal terms. So if you sum of diagonal terms is equal to summation of eigenvalues. You can see? Yeah. So this means that just using eigenvalues, you can argue about a lot about the matrix A. Right? You can argue about a lot of things. You can find the determinant, you can find the trace, you can find other things. So that's why the eigenvectors are characteristic directions. So the argument goes like this, that if you have a data matrix A, right, you find the correlation coefficient of A, right? The correlation matrix. Correlation matrix means what? You take two rows, right, row 1, row 2, you align them in different ways, and if they don't really match, you zero pad them, right? You multiply each element, sum them up. That becomes correlation. And what is autocorrelation? Autocorrelation is that row with respect to that row. Right? Now correlation has maximum value of 1 when the signals directly match and there is no zero padding. Now if you shift, then there will be zero padding and correlation will drop. Right? So you find the correlation coefficient matrix, which means the first element is what? 1, 1 is what is autocorrelation, the data with itself. Then the 1, 2 is what? First row with second row. Then 1, 3 is what? Second row with third row. So that is called the covariance matrix. Covariance matrix. How does different elements of the data vary within themselves? So covariance matrix. So you take the covariance matrix. Now if you take the covariance matrix and you find out the characteristic equation of that covariance matrix. Right? Say, let's say instead of A being the data matrix, A is now the covariance matrix. Right? A is now the covariance matrix. So AX means what? AX means it's a projection of the covariance matrix in that direction X. Now consider that X is the eigenvector which has the largest eigenvalue. If you consider that X is the eigenvector which has the largest eigenvalue, what does that tell us? What? Eigenvalue means what? That has the largest projection. In that direction, it has the largest projection. Projection of what? Projection of the covariance matrix. So if I have the covariance matrix and I have largest projection in that direction, what does that tell about the data matrix? Largest variance. That direction has the largest variance. Right? PCA does this. What PCA does is that it takes the data matrix, finds out the covariance matrix of the data matrix, finds out its eigenvalues, and then orders the eigenvalues in decreasing order. The top eigenvalue is the direction where there is a maximum variance. The second eigenvalue is the second most variance. Third is the third most variance. So these are directions, right? These are directions where you have most variance of the data. Now, if you take the data matrix, forget about covariance matrix. If you take the data matrix and multiply with the eigenvalue, which has the highest eigenvector, no. If you take the data matrix and multiply with the eigenvector, which has the highest eigenvalue for the covariance matrix, what do you get? You get a direction, or you get a projection on a direction that has maximum variance. Right? So if you look at the figure, if you look at this figure, this one, right? Along what direction does it have maximum variance? Does it have variance, maximum variance along the x1 dimension? It does not. You can see a linear correlation between x1 and x2, right? So along the direction E, it has the maximum variance. Why? Intuitively that is the case, right? Because if you find out the projection, if you find out the projection on x1 direction, so if you find out the projection in this direction, then what is the minimum value? The minimum value is here and the maximum value is somewhere here. That difference, so maximum value is somewhere here, minimum value somewhere here. That difference is much less than if you have perpendicular projections on E, right? So this length is much less than this small length. Questions? Somebody has a question?
Normally the hypotenuse
larger than the sides, right?
What happened? The hypotenuse is what?
The length of the points on the line C will be always more than the projection on X.
Line
or
E.
X.
Line E.
So line E will always more than their projection on X. or X.
Yeah, that's how the data is arranged. That's how the data is arranged. So along the direction E, the variance is largest. So if you take the if you represent these data points using a data matrix A, and you take the covariance matrix, find out eigenvectors. The first eigenvector that you get is E. That is the first eigenvector that you get. It will have not first. It will have the maximum eigenvalue. It's not the first eigenvector. It's the maximum eigenvalue that you get for that E. Now let's say you eliminate that eigenvector. What will be the second eigenvector? Perpendicular to E. Okay? Perpendicular to E. That is the next dimension where you have maximum variance. So if for this data point you will have two eigenvalues and two eigenvectors. Right? That is one case. Now that is the case where you are keeping the dimension with maximum variance and you are eliminating dimensions with lower variances. So that is the first argument that we put forth. Right? While discussing PCA, that is the first argument that we put forth. That is the first signal we deleted, low variance. So that's the first way of doing dimensionality reduction, finding out eigenvectors. Now, how many of you are familiar with rank of a matrix? What do you mean by rank of a matrix? So if you have an n cross n matrix, and I say that the rank of this matrix is n minus 1, or rather n minus 2, no, n minus 1, let's say. So if the rank of this matrix is n minus 1, what does that mean? What?
Linearly independent vectors.
What does it mean by linearly independent vectors?
You cannot get another vector with using a combination of those.
Yes. So if I say that a matrix has of dimension n cross n has a rank n minus 1, then that means there is one row or one column that is a linear, that can be expressed as a linear combination of other columns. Right? If you find out the eigenvalues of the covariance matrix of such a matrix whose rank is less than the dimension, then you will see that the number of eigenvalues is equal to the rank of the matrix. Right? So since PCA finds out the eigenvalues of the covariance matrix, it automatically eliminates the dimensions that are linear combination of two or other three dimensions, two or more than two dimensions. So PCA works with these two approaches. First approach is eliminates the lowest, or no, doesn't eliminate, it ranks the dimensions in from highest to the lowest eigenvalues, right? And it also eliminates dimensions that are linear combination of others. That is the principal component analysis method. So now, that is what it is saying. Find the eigenvectors of the covariance matrix. Eigenvectors define the new space. Okay, that is this we didn't discuss. So now there is a new space. What is the new space? Eigenvectors are what? They are directions. They are vectors. Vectors mean directions. So what they are saying is that instead of having the x1, x2 dimension, you look at the data with E and perpendicular to E. That coordinate space. You look at the data in that coordinate space. And in that coordinate space, the E axis is the best one. The perpendicular to E axis is not the best one. Right? So what you can do is you can eliminate the perpendicular to E axis. You can only work with the E axis. Right? Now what is E axis? E axis is a combination of x1 and x2. It's a linear combination of x1 and x2, right? So PCA can also tell you how can you combine dimensions. It not only tells you which dimensions you can eliminate, it also tells you that okay, you can eliminate x2, but instead of having x1, you have ax1 plus bx2. Right? If you have ax1 plus bx2, then you can eliminate x1 and x2. You don't need x1 and x2. You just have ax1 plus bx2. Right? So principal component analysis also tells you that how do you combine the dimensions, the data dimensions, so that you get the maximum variance, and you can only keep that combination, eliminate all the other dimensions. Yes.
This goes against your argument that you're eliminating the source, right?
Yeah, so you are not eliminating the source. That's what I'm saying.
No, you said you're eliminating x1, x2, and just leaving this.
So yeah, you may or may not eliminate, but the main point is that PCA gives you how to combine. That's what it tells you. Any other questions? Yes.
So for suppose if the data was in first and third quadrant, then does it matter if we take plus A or minus A? So like if the data was in like first and
No, only direction. Doesn't matter whether you take plus or minus. So I won't go and discuss any other topic today. So if you have any questions, we can talk about the PCA. But if not, then we can go.